Hello. Hello. Welcome back, everyone. Now we are having a PhD forum with 5 presentations. Chairperson for this session will be Professor Povitro Palchaudhuri. Professor Povitro Palchaudhuri is a professor of computer science with special research emphasis on reliable computer network design, theory and application of two-dimensional cellular automata, statistical analysis of algorithms complexity, fractal technology, genomics with the Applied Statistics Unit, Indian Statistical Institute, Kolkata, India. He obtained his PhD degree in computer science from the University of Calcutta, India. He has more than 29 years of teaching experience. Earlier, he was a faculty in the Department of Mathematics and Computer Science, Claflin University, South Carolina, USA. He has authored one book named on operating system principles and design, and two more are on the way. Mm, I am taking the privilege to ask Dr. Palchaudhuri to chair this session. Sir, over to you.
Thank you, Tanushree, for introducing me. So, in this PhD program, there are 4 submissions which are already completed, which I observed. And there are 5 ongoing presentations. And one general comment I have to make is this: whenever I see different PhD dissertations or these kind of submissions, unless I go into the good published work deeply and broadly means in different things, that the items are not made very clear. So it's a kind of, within a very short time, I have to assimilate so many things for all these 9 different PhD submissions. So beforehand, I want to congratulate the submitted thesis, which I observe very good results have been published. The first one says cyclic properties of cellular automata. And in sequence, there are other 3. And there are 5 submissions where there are some gap of informations. There are some want of informations on my side also in writing. That's why I could not complete my observations in some of these, at least in 2, in the latter half. So let me start with cyclic properties of cellular automata. The Sukanya, probably the Sukanya, or who will be the Sukanya Mukherjee will be the presenter.
Good morning, everyone. I am Sukanya Mukherjee. Today I am going to speak on my PhD dissertation topic, Cyclic Properties of Cellular Automata. I did the work under the supervision of Dr. Sukanta Das. In our work, we use one-dimensional three-neighborhood binary cellular automata. Let's move to the topics what we targeted and tried to cover. First, we focus on the cycle structure computation of cellular automata. Now, what is cycle structure? Cycle structure of a CA actually determines the number of cycles along with the lengths. Here, we started the work with the problem statement of configuration reachability problem, which is also called as CRAPE, where for a given CA, the source configuration, let's consider in this example 0001 and the destination configuration 1011 are given. So, CRAPE determines whether there exists any path from source to destination. Now, this CRAPE problem can also be connected with cycle identification. How? Because if the source configuration and destination configurations are same, then we can say the corresponding configuration in cycle. Now, in this example, you can see the configuration space of the corresponding C is represented by the configuration transition diagram. But the configuration space can also be represented by other different tools. So here in our work, we take the help of reachability tree. Now, what is reachability tree? Just the configuration space and the connection among the configurations represented by this pictorial view of the tree. Here, every actually each of the sequence, edge sequence representing the configuration. So if I consider just 0100 as the configuration, you are requested to look the edge sequence E00, E1, E11, E22 and E34. This is actually representing a configuration, and along with that some of the edge sequences also representing the sequence of RMTs. Now question comes, if the source configurations and destination configurations are same, how do you understand from the reachability tree? So definitely each of the edge sequence should be in a loop. So if you look at the level 0, E00 is connected with E10, and again there is a loop, a link from E01 to E00. So what I try to say, each of the edge sequences corresponds to 0100 will be part of some loop, and that loop is formed level wise. So this type of loop is called as cross-link for the level. Next, it may happen the corresponding configuration is only creating the loop, or the edge sequence is creating the loop with itself, and it's actually called as self-link. And the collection of self-link, that means in this example all 0 is actually forming a cycle of length 1. Now, from there, we actually targeted to see if the configuration is not reachable from itself. That means the source configuration and destination configurations we given as same, but they are not reachable, but that is not reachable from itself. So what does it mean? Actually, that type of configuration called as acyclic configurations. And you can understand, as we are interested in cycle structure computation, so we not interested about the acyclic configurations. We anyhow want to remove the acyclic configuration. So let's take the example here. Here 1010 is a configuration. The question comes, is it reachable from itself? So just look at the edge sequence of 1010, E001, E11, E25, and in this case E310. Now E310 is called as non-reachable edge. Now what is the significance of non-reachable edge? It is not connected, it cannot be connected or linked with any other edge. Why? Because it's not carrying any RMT. So in this way, we can say 1010 is just a cyclic configuration. So similarly few properties we found from here. Here also we can say 1010 in this example is not a cyclic configuration, not reachable from itself. Why? Because one of the associated edge of the edge sequence, that is E2.5, is connected or linked with such edge which is non-reachable. And this is also another property by which we can say 1101 is non-reachable, where the one of the edge of the edge sequence corresponding to 1101 is linked to such edge which forms only one loop. From there you cannot anyhow coming back to the corresponding edge, that is E2.6. So What is the contribution of this? We can understand by this we can remove the acyclic configurations uh, just in one or two steps. So our objective is to figure out in every level of the reachability tree which are not useful for my cycle computation, and these are the steps. So in every level which links we keep, only which will be involved in cross link and self link, all other will be discarded. So if I try to figure out the cycle structure of this given ca, so in that case what will happen if we do not follow such type of things? We have to explore the entire tree. This is a 4 cell ca, we have to explore up to level 0, level 1, level 2, level 3, and up to leaf level, and at the leaf level we will get total 60 links and we have to traverse it. But here you can see some of the links are discarded at level 0 or level 1, and that links will not be processed links. That means their inherited links will not be processed next, because these are the part of acyclic configurations. So in this way, actually at the leaf level we use only 7 links, and from there we computed the cycle structure. And these are some of our experimental results. Now question comes, what about reversible CA? Do we get acyclic configurations? No, never. We do not get any acyclic configuration. So if we just look at this example, this is a case of reversible CA. Here we try to figure out some disjoint components in the reachability tree. Okay, and these disjoint components are what? These are called as subtrees. And again, we try to figure out the number of cycles along with the cycle lengths in the disjoint subtrees, and that type of thing is called as partial cycle structure. So our target is to figure out the cycle structure of a CA by the help of partial cycle structure. So in this example, you can find this is one subtree, and we can find the partial cycle structure of this. Similarly, we can find the partial cycle structure of this subtree, and these two subtrees are connected and actually considered as one disjoint component. And here also we can find the partial cycle structure, and ultimately the cycle structure of the given C is computed like this. Now why we are just doing the partial cycle structure? What is the implication of this? Actually, we want to find some similarity among the subtrees, and that is we termed as isomorphism in subtrees. So if two subtrees behave like same means same cycles, same length cycles they are producing, so we can just explore one of them. So for that we use the concept of identical links. If two links are identical, we just explore only one of them. So let's take an example. This is an example. Here we divided into 8 subtrees, and we can find a subtree 3.0 and 3.4 are identical. So we only explore one of them, 3.0. We get the partial cycle structure, and the same partial cycle structure will be applicable for 3.4 also. Next, move to this here, 3.1, 3.7, 3.2. These are connected components. Okay. And another connected components 3.3, 3.6, and 3.5. Now, these two are isomorphic. Only we explore one of them, and we will just get the another one also. In this way, we find out the cycle structure of CA without exploring the entire reversible CA. Definitely, it's not applicable for all possible reversible CA. For few cases, for some cases we can find. And one more thing I want to add here, we just compare the disjoint component or disjoint subtrees. Even within a subtree also, we figure out the isomorphism. So these are some of the results. Next, we move to cyclic spaces of reversible cellular automata, which is mainly depending on the concept of decomposition of cycle structure. Now, what is the meaning of decomposition of cycle structure? Here we focus on reversible cellular automata. Let's consider the two diagram. If we look at the left side diagram, definitely it's using 4 cells here, and the right hand side 3 cells here. Now, what we are finding, the cyclic space of the right hand side C is contained in the cyclic space of the left hand side C. So, and one more thing I want to say, the cycle structure of the both CAs, you are finding one thing, that is the cycle structure of the 4 cell CA. What are the length of the cycle 1, 2, 5, which are also present in the left hand side, right hand side CA. So what we try to say, one cycle structure will be decomposed. Cycle structure of N cell CA can be decomposed into the cycle structure of N1 cell CA if every cycle length of the n cell CA is multiple of some cycle length of n1 cell CA. So it is holding the property of decomposition. Here also we can find a beautiful property where in one CA, both two different CA's cyclic spaces are contained. But in this case we are not finding any such type of things. Now why? Because you look, the cycle length is 11, and which is a prime number, and here the CA size is 4. So we know, all of us know, 1 should be the multiple, 11 should be the multiple of either 11 or 1. So definitely we cannot decompose it. So depending on this type of concept, we actually categorize the cellular automata into mainly broadly two categories: reducible cellular automata and irreducible cellular automata. In case of reducible cellular automata, actually we look, their cycle structure can be decomposed, whereas in irreducible it can't. Uh, Now, reducible cellular automata can be two types: strictly and weakly. Let's move to the point. Strictly means what? Actually, the entire cycle structure will be divided into two parts. If I just move back here, this is the example of strictly reducible CA. Now, what is weakly reducible CA? This is the example of weakly reducible CA. That means the cycle structure can be decomposed, but not like this. If n is the length, size of the CA, it's not mandatorily n should be written as n1 plus n2. That can be written for strictly reducible CA. But if n is the CA, in case of reducible or weakly reducible, for weakly reducible CA, there exists some n1 length CA whose cycle structure, whose cyclic space is contained in the cyclic space of n. So we figure out some of the properties, and by these properties we actually identified whether the given C is strictly reducible, weakly reducible, or irreducible. I just pointed few of the examples. So you can find the first one is the strictly reducible. Why? Because this can be broken into two CS. The second one also can be broken into two CS. The third one is not strictly reducible. Why? Because 176, that can be written as 11 into 16. And so if 16 length cycle is there, so 5 bits CA, and 11 length 4 bits CA. So at least 9 bits CA should be. But here it is actually 8 bits CA. So this type of examples shows this is not strictly reducible. Next two are weakly reducible, and the last three are irreducible, where 193 is a prime number, we cannot break it. 255 is a maximal length CA, and 243, just try to figure out 13 and 243, this is also irreducible. How can we say these two are odd numbers? Two odd numbers if I find, so in that case that is also irreducible. So these are few examples and few results. Next, I move to reversible cellular automata with large cycles and their applications. So what is our target actually? If L is the length of a CA, we want to develop a CA of n size which can generate a cycle of length at least L, and n should be as small as possible. Now, what is the best thing? Maximal length CA, but all of us know for maximal length CA, generally we use the linear CA and primitive polynomial. So the availability of primitive polynomial is limited, and generating of primitive polynomial is also exponential. So what we did actually, we generate small size component CAs stochastically. How? I'm just moving to that part later. So after that we just concatenate this CS. How we concatenate? Just I showed you actually. If I find two cycle structures, we can find the resultant cycle structure by the help of LCM and GC just in the strictly reducible CA. So we get two CS and concatenate. Now what CS we are concatenating? This actually the second step. Select small size CA, we must consider C of size n1 with cycle of length larger than 2 to the power n minus 1, and that we are doing using the stochastic manner. For that, what we do it actually, here we take the help of here we take as input the reversible ECA. and it is already the rule set already is available. So how we generate the reversible n cell CA, non-uniform CA. So here what we did, we categorized the rules into 4 categories: completely dependent, partially dependent, weakly dependent, and independent. The reason is what, here we just dividing the rules depending on the influence of the neighbors. That means the rules which is completely dependent, they are highly dependent on their neighbors, partially dependent, less with respect to completely, weakly, very small dependency, and independence means zero. And we can see from the observations also, if more dependence, then there is a tendency of getting large length cycles. So keeping this thing in our mind, we developed CA stochastically, but it's not guaranteed always we will get the large length CA. So what we did actually, say 3 to 30, these size CAs we have taken, and we computed their cycle structure. We consider only those CAs whose cycle lengths are greater than 2 to the power n minus 1, and after that we concatenate. Even after concatenation, it's not guaranteed we always get the large length cycle. So what we did, we concatenate in such a manner where the cycle lengths are co-prime. So after that, is in that case we use some evolutionary strategy, which is not just the it's just the some variant of genetic algorithm. Here we use the fitness score. Fitness score means what, fitness score should be here we use the actually minimization function. Minimization means what, definitely the CSI should be minimum. But the thing is that when we are producing the offspring, we are not using the just genetic operators like mutation and crossover. Here, rather, we try to find the best possible results from the previous generation. That is 30%. 50% we are doing just by mixing. Mixing means what, we take the good parents. Good parents means what, those who have the less CSIs. That parents we have taken, and their good features or significant features we have taken. Now, there may be a question, what is significant features? Actually, we select those type of cycle lengths where the factors are less. Factor less means what, they actually helping to find the co-prime numbers, and then we do the LCM, and ultimately we get some results. So actually these are the these I have already shown. So stochastic manner what we have developed, that thing we are getting here, but that's restricted. We do the computation up to 2830. So here we are here actually we use the evolutionary strategy, and we get the results. Next we move to reversible cellular automata, a natural clustering technique. Now, here I want to tell you one thing. If we look at reversible cellular automata, what we get, the cyclics, in the cyclic space, all the configurations connected in such a manner, that means they are reachable from each other. So what does it mean actually? Every cycle can be considered here as clusters, and the reachability properties also holds here, that is called as the locality property. That means one configuration is reachable from a set of other configurations. So this property actually leads us to think, can we use reversible CA for clustering? Yes, when we do the clustering, we have to keep two things in our mind: desired number clusters and less intra-cluster distance. So what we did here actually, initially we started with non-uniform cellular automata, again one dimensional 3 neighborhood binary non-uniform cellular reversible CA. So what we did actually, we can understand one thing, to get a desired number of clusters with less intra-cluster distance. Intra-cluster distance means within the cluster the very similar objects are there. It's not very easy. So what we did here, we used some iterative approach, and we merge the closely reachable clusters. I will go to that part later. So here, what we do it for CA-based clustering, we use the same type of same type of CA. We generate large length cycles, and even we do in this way, the question, do we get always the correct answer? No. Good result clusters? No. So that's why we move to the concept of these three steps where we actually rank the rules. Here we rank the rules depending on the intra-cluster distance. Intra-cluster means here we mainly focus on state change. Where the state change is less, we are selecting those type of rules. But it's again true, if we take only those type of rules, we do not get the large length cycle. So we have to follow the strategy what we mentioned previously, and along with that we have to rank the rules. So here what we do, I want to just take an example. Total number of objects is 150, desired number of clusters 2, number of attributes 4. Which type of attribute we have taken? Quantitative attribute. Now for quantitative attribute, we actually divided into three space. Uh, which are very close, that is represented by 0 0, next close part 0 1, and next close 1 1. So why I am taking this 0 0 and 0 1? If you find the distance 1, 0 0 and 1 1 if you find the distance 2. So here actually the CSIs will be 8. Why? Because for encoding the attribute we are taking two bits, so total 8 size C I am taking. So here objects are 150, but I want to tell you, just look at uh, here if you look if you do it, then you can find only 18 distinct configurations we get, 24 distinct configurations we get. That means 150 objects I am not clustering, I am mainly focusing on 24 configurations. And here we can say every configuration called as primary cluster. So initial level, all the configurations are belonging to a cluster. Then we design a auxiliary CA. What are the properties of the auxiliary CA? It will produce large length. Second thing, it will maintain the less intra-cluster distance. From here, we can find four different cycles, and what we will be finding in the auxiliary clusters, which primary cluster is belonging to which auxiliary cluster, and that we have represented. The small c1 is 100%, that means every member of c1, definitely here every member means only one member in c1, in capital C1. In this way we distributed. Ultimately what we did, actually if we look at capital C1, those who have the highest participation, we are merging them. So here all of them have 100%. So actually from 24 clusters we get only 4 clusters. Am I reaching my goal? No. Next is, again we generate another auxiliary cluster, auxiliary C of same size, but here the auxiliary clusters 6. Now here what we can find, if we look at C2, 100% participation, and okay, 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 okay. Okay, okay. 100% and 34%. So we actually, sorry, 100% and 63%. So we march C3 and C2. Similarly, 100% and 34% we march C1 and C4. And ultimately we reach to the goal. And here we have just given few of the results. Okay, one more thing I want to mention, other than non-uniform CA, we did the work using uniform CA where we consider the 5 neighborhood architecture. So these are the results, and here also we can show one of the properties of clustering. If we reorder the features, then also we can get same type of results. And these are few of my future work. Actually, though we try to reduce the complexity of cycle structure, but it's not for arbitrary CA, so that we have to focus, and we mainly concentrating on next focus is clustering for large dimensional data. Definitely large cycle generation for D state radius we are restricted to here just on ECA. So these are the things, these are few publications of my work. Thank you.
Hello, hello. Is it audible?
Yes, sir. Thank
Yeah,
you.
okay, okay, okay. initial phase, what you showed us, the in some non-reachable states, non-reachable configurations, right? You are trying to find the non-reachable configurations. Suppose n getting larger and larger, and whether you are in a position to find all kinds of non-reachable configurations, this is one question.
Okay.
Would you like to answer? Please.
Yes, sir. Actually, what we are doing in reachability tree, we are moving level by level. So in every level, we find, say, start from level 0. Two edges are there. Is there any non-reachable? No. Then we can process next level. 4, we are getting which one will be non-reachable. We just remove it and we will not process next. So in this way, we can find the non-reachable edges, which will actually represent the non.
Quite moderately large, you are in a position to find all non-reachable states.
Yes, sir. Actually, the number of non-reachable configuration is also exponential.
Even n is finite. How n is finite? So
This is
finding non-reachable states, you are saying exponential, right?
sir. Actually, in every level we do the process. Yes. Yeah, it may happen nowhere non-reachable, only in the leaf level non-reachable. That you are trying to say. Yes, in that.
CAs which are not reversible, we surely find so many non-reachable states. You are agreeing, right?
Yes.
Okay. My another question is whether you have explored for moderately large n, suppose n 5, 6, 7, 8, 9. All sorts of non-uniform CAs have you explored? All sorts of non-uniform CAs have you explored?
Sir, for cycle structure computation,
Yes.
sir, for reversible or irreversible?
No, both.
Both.
For
Okay,
both.
sir. Okay, I'm trying to give the answer. For irreversible CSR, using this technique, we actually can show you some of the results. But this is special case, not for any arbitrary CA. Again, I am repeating. And for reversible CA, I have to mention one thing, sir. If the CA consisting of 9150, my scheme will not work.
Okay, so
That
I was just wondering, not all sorts of non-uniform non-uniform CAs. It's a future work. All sorts of non-uniform CAs will be a future work, right? You have not explored it. Okay, thank you.
Thank you, sir.
So, okay. That is one online question, I suppose. Questions. Yes. Online questions, please. Hello. Any online question, please? Oh, Professor J.M. Gennaro, R.K. Goel. Professor R.K. Goel, can you put it, please?
Sir, I have written the question in the chat, probably because I am not audible. Am I audible? So the question is that is there any specific reason for taking the length of the configurations in the initial part of this presentation as 4, means such a low value? So are you taking such a low value to keep the reachability tree small, or is there any other reason? And what could be the effect on the conclusion stability of this study if you take the larger values of n, say 32 or say 64?
No, your call.
That's an example I have given to just present in PPT. That's why I have taken the 4 cells here.
Okay, yeah, thank you.
Thank you.
I'm just wondering, any other question, online question? No. So in the event of no, so I invite the next presenter.
Thank you, sir.
Next presenter, the title is Distributed Computing on Cellular Automata with Applications to Societal Problems. Mr. Souvik Rai. I'm sorry, maybe Dr. Souvik Rai.
Thank you, sir. Uh, so let me share my screen. So my skin is, I think, hope visible, and I'm audible too. Mm. Okay. The title of my thesis is Distributed Computing on Cellular Automata with Application to Societal Problems, and under the guidance of Professor Sukanta Das. And in this 15-minute time, it is not possible for me to explain all the theoretical details, but I'll try to attend more on what are the thoughts, why we are doing the things, and what are the outcomes, and what are the future possibilities from it. So, kind of motivation is during my MTech, I came to know about Cellular Automata. During that time, according to my socio-political life, I was searching for the definition of democracy. Then I came to know about Cellular Automata, kind of a democratic model. And then I started doing research in Cellular Automata during my MTech, and suddenly I've started doing PhD with the topic of the distributed computing capability of Cellular Automata. And if you think about the history of mankind, also computer science, so if you, this is a popular example, if you see a flock of birds, we try to think that there should be some leader in the front, and the leader will lead the flock of birds. But in reality, in nature is quite distributed. In nature, the birds actually interact with each other locally, and they came up with some global decision. So if we think the journey of computer science starting from Turing, there are some sense of centralization in Turing machine also. Then distributed computing came into picture, and with the journey of this Cartesian approach, Cellular Automata is also came in picture. So in this thesis, there are two parts. First part, I'll skip. I'll just skip the definition of cellular automata. Here we are using two-dimensional and one-dimensional both cellular automata. In case of one-dimensional, we use 3 neighborhood or 4 neighborhood, and in case of two-dimensional, we use 1 neighborhood and more neighborhood. So in the first part of I'll talking about some mathematical engineering. Mathematical engineering means we human beings trying to develop a cellular automata, and from that cellular automata, we're trying to solve some distributed system problems. And so here, the ability of the developed cellular automata is something bounded by our cognitive ability of thinking. So we can think about computation. In computation, there are some input and output, and there will be a solution path, and according to that, that will be a algorithm. And in cellular automata, you can think about initial configuration is a input, and then there will be some intermediate configurations, and the final configuration is the output. You can think we can consider fixed point as a final configuration in general, and the rule is actually the algorithm. And here we try to solve two problems, specifically distributed mutual exclusion problem and spanning tree problem, both for anonymous instance, because in cellular automata there are no numbering of cells. So these two problems for anonymous instance, And for the first problem, so first problem, distributed mutualization problem, this is kind of a super problem of leader election problem with some fairness and liveness property. And we developed CA with 6 states. The meaning of the states are ideal, requesting for this critical section, which is the fundamental thing of this mutualization problem. Cells which are not interested in critical section, which are, for them permission is granted, from them permission is not granted, and who are actually executing the critical section. So we are actually taking 3 tuples of cells, one for these states and 2 tuples for the priorities, because in mutualization problem different cells are targeting to achieve something and they are associated with different priorities. So now the thing is that this is kind of symmetry breaking problem, and for as a whole for any cellular automata it is not possible, and this is a known result. And so we differentiate all possible initial configurations in cellular automata with 6 categories. One is uniform, where everyone is asking for critical section and it is not possible to solve. One is symmetric, where the same thing is repeated again and again, and again it is not possible to break the symmetry. Hello, I'm audible? Hello, I'm audible or not? Please, someone.
Yes, Dr. Roy, you are audible.
Okay. So then for uniform and symmetric, we have proved that it's not possible to solve. Then we take temporally unique configuration where each and every cells are asking for critical section are associated with a unique value of priority, and it is possible to solve. We have developed an algorithm for it. Then we consider tightly coupled configuration where the cells asking for critical section with same priority are in a cluster. So this is the definition of this tightly coupled. So is it possible to solve? We have developed CA for it. Then moderately coupled where the cells asking for critical section with same priority are forming again a cluster, but in this cluster there is possible also idle cells which is not asking for critical section. So it is also possible for solve it. And the last type of configuration is loosely coupled. For it, we neither able to solve it, we neither able to prove it that it can be solved or cannot be. But intuitively we can say we cannot solve it. So this is the first problem, mutualization problem, and this part is published in Journal of Cellular Automata. Then we have considered the distributed spanning tree problem. So in spanning tree problem, we have taken grid graph, and initially each of the cells, node representing cells, there are 2 type of cells in this. If you try to map this thing in cellular automata, 2D-dimensional grid, in considering one neighborhood. So each cells, node representing cells initially are the forest. Then there are 2 phases of this computation. One is going of trees. We grow each and every nodes initially following a specific priorities. So suppose left one, if there is a left node, then it will be first, then up, then right. So that's the priority. So growing of trees, then after growing of trees, will create small spanning trees of some of part of it. Okay. So now of the task is identifying the bridging node for connect this small forest. So this part is hard. First part is just moving with the priorities, connecting with the neighboring node representing cells. It is easy. So the next part, it is hard because we have to identify which one are the internal node within this small spanning tree and which are the external node, because we have to delete the internal nodes and we have to select one external node out of the external nodes. That's some following is fashion that there should not be no cycle. So for this small part, suppose this is the small part, there are 1 internal node in red, 2 external node in blue. So we have to identify which one is the internal node, which 2 are the external node. We have to select one out of them. So we just think this part of the small spanning tree as a highway with 2 lanes, and we rotate a token. We identify the values plus minus that who are the top one, who are the low one, and we can identify the internal and external node. You can just delete the internal, connecting with the external with some priority again, and we'll get the spanning tree. So for this computation, we have taken 36 states, and the computation time is n log n, and this part is published in Journal of Computational Science. And so the thing is that up to that part, I was in the initial days of my PhD, first 1 or 2 years. Somehow these algorithms are published. The algorithms are good, but my supervisor is not happy with me because these algorithms are somehow mechanical. There is no magic in these algorithms. There is something not happening suddenly that we just evolving a Cellular Automata, and we came to know that okay, fine, this is something evolving, and suddenly we can able to solve, suppose, some density classification problem. So that's not the situation. We are with our cognitive ability, we are trying to build some Cellular Automata. We can able to solve the problem, and the Cellular Automata with 36 cells, there are lots of complications, and Cellular Automata is famous for simplicity. So next, we try to explore Cellular Automata from natural science perspective, try to evolve the system, a simple Cellular Automata system, try to understand the inherent capability of the system for solving distributed system problems, or we can think about nature as a society, or nature as a example of distributed system according to these problems. So in this part, first we explore asynchronous Cellular Automata. Again, I should mention that initially I am talking about this flock of birds and the distributed system and Cellular Automata, all these things. Now the situation is that if you also consider the decentralized model as Cellular Automata, there are a lot of centralization in this model also. In our society also, if we take the example of socialism or capital, if we in terms of capital, if you think the democracy, then there are also lots of centralization in terms of caste, gender, all these things. So in case of Cellular Automata also, this is true. In Cellular Automata, there are cells updated together, there are synchronization, all cells following the same rules, there are centralization, there is a specific grid structure, there are centralization in this thing. So we want to break that centralization in Cellular Automata itself and try to understand the inherent capability of that system for computation. So first we have explored the asynchronous Cellular Automata, convergence dynamics of asynchronous Cellular Automata. We have identified which rules are convergent. Then within this convergent rule, we are trying to understand what are the basin of attraction dynamics of the convergence system. And we have identified 3 kind of dynamics. One is, we name these dynamics as cloud system. So one is asymptotic cloud system, where all the initial configurations may go to both of the attractors. Here I'm giving the example with 2 attractor system, but it is also true for multi-attractor system. So in the first case, all the configurations, there are probability they can go to any of the attractor. And the second case is, so this eccentric cloud is something like the clouds in our sky, cloudy sky. Then the partially eccentric system, where some initial configurations are in the red, may go to both the attractors in black, but some initial configuration are dedicated to particular attractor in blue. So you can imagine this system as a electoral model of parliamentary democratic system, where there are some dedicated voter of a particular political party. So you can think about them as these blue things, and this red thing are the voters, sometimes this party, sometimes this party. So these are the cloudy voters. Okay, and the last one is some deterministic cloud system, where all the initial configuration move to a particular attractor. But in the deterministic system also, there are non-determinism, because for a convergence journey, they will follow different paths in different run. Okay, so these are
Souvik, you have 4 minutes time, please. 4 minutes time.
Okay. Thank you. So these are kind of electrons. So we have theorized the system, and also in the eccentric cloud system, we are divided into 2 parts, biased and unbiased system, and suddenly to come up with that this unbiased system are good for density classification problem. So we are exploring the inherent capability and suddenly we are getting up some result for solving computational problem. We are not designing this CA, we are just exploring the rule space and getting some result. The second part is we are explaining the precision of attraction dynamic of reversible CA. We differentiate them into two classes. One is fully exposed, one is partially exposed. In fully exposed, in the reverse, in the cycle, all the configurations are equally probable. This is an example of fully exposed. And in partially exposed, some configurations are hidden. And this fully exposed system is good for randomness enhancer. Later we have designed randomness enhancer with this fully exposed system, and this partially exposed system is good for cryptography. We are now trying to design cryptography with this partially exposed system. Then we have explored, we introduce delay and information loss in the system. We will get different kind of possibilities of phase transitions, different in space-time diagram, and also in the quantitative result. Then we also explored this delay sensitivity for game of life. And finally, with this delay sensitivity, we will try to model the dynamics of riot, where delay acts as a presence of communal element in the society, and probabilistic loss of information act as a anti-riot population in the society. We have taken the genetic behavior of this delay sensitive system, and we consider that the riot dynamics have two phase. One is spreading phase and one is diminishing phase, and the candidates with phase transition behavior are rule ACA 18, 26, 50 and 148. Then we have collected the data set for one riot event in Bengal, a Badira event, collected the number of police attacks and all this information, and according to that number of area affected by riot, we quantify riots. And rule 26 is the best fitted candidate for this modeling this riot dynamics. Not only for this riot, we have also explored the 2011 French riot, 2015 French riot, 2011 London riot, and we say that this sudden up and sudden down is rule 18 can able to model it. Slow up and slow down, rule 154 can able to model it. So all these rules are also applicable for not only for this particular case study we have done, for other cases also, and this is also reported in the paper in complex system. So these are the publications, and I want to say thank you not only my supervisor Sukanta Das, also Professor Biplab K. Sikdar and Professor Souvik Mukherjee. The beautiful journey I have lived in ISTC 4, that was the most beautiful year, and we have come up with the thoughts of computation with noise from this beautiful journey. And now I am trying to exploring the stochastic cellular automata computation from this noise, all these things. Thank you very much.
Thank you, Souvik. For my more understanding, may I request you about the last latter part, the communal riot dynamics, where delay sensitivity is used. Please explain what do you mean by delay sensitivity, and how you are inferring that this is suitable model for communal riot dynamics.
So the first of thing is that modeling riot like mathematical phenomena, we're trying to keep things simple, so we can able to add more parameters. There are more parameters in riot, but we have taken two parameters. One is the presence of anti-riot population, and the second one is the presence of communal organization in the society. So the two parameter, one is information loss. When the cell interacts with each other, some information will be lost. Okay, so that is kind of the presence of anti-riot population. And the delay is when the information will be shared, there will be some non-uniform delay. Maybe after the third step, it will get the information, the neighboring cell. So that is the meaning of delay and information loss. And we start with a single cell. Suppose this is the origin of the riot, and we observing the generative behavior of the system. Okay, and we quantify according to the riot event. There are some standard policy of quantifying riot event by social scientists mostly. So following them, we quantify them. Now for this cellular automata system, with this rule, we try to understand the generative behavior of them. And obviously, the rules should have two features. One is they should grow in both sides, all sides. They should not flow one side. So the information should be shared in all sides. And second is there should be two phases. One is growing phase, one is sinking phase. So there should be some phase transition behavior in terms of statistical physics. Okay. Then with dynamics, this the all these features passed by the rules. Then we have analyzed their dynamics, quantifying the number of ones and number of zeros. Some rules are showing some sudden up and sudden down dynamics. Okay. And in terms of riot, few riots shows this kind of dynamics, sudden up and sudden down. There are cases where slow up and sudden down. So this type of cases are there. In suppose in case of London riot, there is a sudden up and sudden down in 2011. So our rule 18 can able to model it. But in case of the case study we have done for Baduria riot, this is rule 26, which is sudden up but slow relaxation. So this this is the procedure we have followed here.
Okay,
Is
thank
it
you.
clear, sir?
I invite other questions, online questions. Any online questions? Yes, Professor Goel, please go ahead.
So,
Professor
Dr.
Goel, please.
Yeah,
Yes.
thank you. So, Dr. Souvik, did you coin this term asynchronous CA, or was it already there in the literature?
There are lots of versions of asynchronous CA. Breaking the synchronicity is asynchronous. So there are lots of definition of asynchronous CA. We have considered fully asynchronous CA, where at a time one cell will be updated, and this is equal to so with the atomicity property that no cells together will be updated. So that's kind of version.
Okay, thank you very much. Very nice talk. Thanks.
So Souvik, thank you for your presentation.
Thank
so
you.
Let's go to the next presenter.
Hello, am I audible?
The next presentation title, Theory and Application of Cellular Automata for Detection and Mitigation of Hardware Trojan Attacks, Targeting Cache Performance in a Many Core System. Probably Suvadip Hazra. Suvadip Hazra is the presenter.
Yes, sir. Am I audible?
Yes. Please go ahead.
Good morning, all. I am Suvadip Hazra. I have done my PhD under the supervision of Dr. Mamata Dalui. Today, I am going to present my thesis on a topic, Theory and Application of Cellular Automata for Detection and Mitigation of Hardware Trojan Attack, Targeting Cache Performance in a Many-Core System. This is the outline of today's presentation. At first, I will introduce what is hardware Trojan. Then I will discuss the motivation behind this task. Then I will discuss the organization of our work element. Then I will discuss our 4 work. That is, first one is synthesis of high-bit MSCA. Then I will discuss 3 potential area of hardware Trojan insertion. That is, coherence exploiting hardware Trojan, memory transaction inducing hardware Trojan, and cache replacement policy affecting hardware Trojan. And at last, I will conclude my thesis. So what is hardware Trojan? Hardware Trojan is nothing but malicious modification of IC design, and this can be done by adversary during IC design or fabrication phase. And purpose of implanting hardware Trojan may be different. Either it can be degrade system performance, or it can provide some covert channels or backdoor through which the sensitive information can be leaked. So this is the basic block diagram of a hardware Trojan, and it is activated by certain triggering condition, and after activation it will cause some payload. So basically, hardware Trojan are categorized based on two mechanisms, that is trigger, activation of the Trojan, and payload, that is effect of the hardware Trojan. And conventional way to detect hardware Trojans are two types, that is logic testing, and another one is sidechain analysis. In case of logic testing, a test vector is generated to activate some unknown Trojan and propagate the Trojan effect to the output port and observe it. And in case of sidechain analysis, a golden IC is required to observe some difference in certain parameter like path delay, power consumption, etc. So motivation behind this topic is, so hardware Trojan is emerged as a serious security threat for the government and industry's identity sector, and effect of the hardware Trojan also severe. For a time critical system, degradation of system performance is a critical issue, and it also leaks secret information. So that is also a critical issue. And to perform the complex functionality, modern day processor implant more number of core, and which consist of billions of transistors, and which make them more vulnerable to hardware Trojan attack. And we know that conventional post-manufacturing test perform poorly to reliably detect hardware Trojan attack, because during the post-manufacturing test, the hardware Trojan may not be activated. So a perfect solution which can reliably protect against hardware Trojan attack of all types, forms, and size is extremely difficult to achieve. So our objective of this work is, so design and implementation of different cache performance affecting hardware Trojan for a real-time Minicore system, and then evaluate the effect of the model Trojan in the performance of a Minicore system. After that, we have developed some unconventional solution to detect hardware Trojan. Mainly, we have utilized cellular automata-based solution, and we have also proposed some mitigation technique to mitigate the Trojan effect, and characterization of CA rule that can be building block for special class of irreversible CA that can be employed for the design target design. So this is the organization of our work element. This consists of two parts. First one is CA theory, cellular automata theory development and application of CA in hardware Trojan and detection and mitigation. So in CA theory development, we have characterized the CA rules. We have synthesized the MSCA in exponential time. Then from the algorithm which can synthesize MSCA in exponential time and consider this as a building block, we have synthesized MSCA in a linear time. And in case of hardware Trojan insertion, we have considered three potential area. First one is cache coherence mechanism. So first hardware Trojan model will affect the cache coherence mechanism of a system. Next one is memory transaction inducing hardware Trojan. For these two hardware Trojan model, we have considered cellular automata based solution to detect and mitigate the Trojan. And the last one is cache replacement policy affecting hardware Trojan. This will affect the replacement policy of a cache system. And for this one, we have developed the mitigation technique, that is adaptive replacement based solution. So this is the basic of cellular automata. Cellular automata is nothing but a finite state machine which was developed by von Neumann in 1950s. In cellular automata, each cell will be updated in every clock cycle, and the next state of the cell will be dependent on its neighbor. So this is the basic structure of two-state three neighborhood CA, where the next cell logic is dependent on present state of the cell itself and present state of the left neighborhood and right neighborhood cell. So combination of present state is known as RMT. So 0, 1, 1 is the third RMT, and next state for third RMT for rule 15 is, for both rule 15, 254 and 255, next state of RMT, third RMT is 1. If the CA are employed with the same rule, then it is known as uniform CA. Otherwise, it is a hybrid CA. So in the state transition behavior, a set of state will create a cycle. So that is known as attractor. For a uniform CA that's configured with rule 16, 0 is the attractor state. And depending on the attractor, if there is at least one fixed point attractor, then it is known as single length cycle attractor CA. For a single SLCA, there may or may not be multi-length attractor. multi-length attractor may or may not be present in case of SLCA. So one special class of SLCA is SACA, where there will be only one fixed point attractor and there should not be any multi-length attractor. So uniform CA with rule 16 is a example of SACA. And if there is more than one fixed point attractor, it is known as MACA. So uniform CA with rule factor 38 is a example of MACA. This is also example of a TACA because this particular rule has creating a two graph, both having one fixed point attractor. So it is also example of TACA. So in this work, we have utilized a graph-based tool, that is next state RMT transition diagram, to get more insight into state transition behavior of a SLCA. So NSRT diagram for a uniform CA already present in the literature. For this particular work, we have utilized NSRTD to for the non-uniform CA. So this is the step for computing NSRTD. So first step is to compute the next cell RMT. We can get the next cell RMT using this rule. Ti plus 1T is indicating the NCR of TIT. So we can get using this formula for the next cell RMT. So NCR of RMT1 is nothing but 2 and 3. In the same way, we can get the NCR of all these RMTs. So after computing NCR, the next step is to compute the or identify the NSR, next state RMT. Suppose XYZ is indicating the RMT of rule RI, based on which the I cell rule will change. And LRR is indicating the I minus 1th cell and I plus 2th cell. And NCR of XYZ is indicated by DL, D, and DR. For a two-state null boundary CA, the following condition will be always satisfied. For the first cell, DL and X will be always set to 0. Similarly, for the second cell, intermediate cell, second last cell, and the last cell, this condition will be always hold. Suppose we are computing the NSR using this hybrid non-uniform CA. So suppose we are computing the NSR for RMT1. So as we already discussed that for first cell, X will be always set to 0 and DL will be always set to 0. So next state for 001 with rule 180 for RMT1 is 0. So this state will be 0. Similarly, this state will be 0. Next, this can be 010 or 011. So we have to consider the RMT 2 and 3 with rule 52. For rule 52, RMT next state for RMT3 is 0 and RMT2 is 1. So it can be either 0 or 1. So NSR for rule 1 is it can be either 0 or 1. Similarly, we can get the NSR for rest of the cell. So all the NSR are listed with this hybrid CA in this table. Next step is to compute NSR sequence. As we discussed, for the first cell, the NSR for 0 is 0 itself. So it is creating a self loop. NSR for 1 is 1 itself and 0. By performing union operation for all the NSR sequence, we are getting the NSRSG for cell 1. In the same way, we can get the NSRSG for rest of the cell also. After computing the NSRSG, the last step is to compute NSRTT. By considering the compatibility class, we are getting exactly two path or NSR sequence, and both are correspond to fixed point attractor. So this is an example of a TSA. To find the simple cycle in NSRSG, we have developed two algorithms here. So first algorithm 1 will accept the rule vector, the length of the CA, and 8 RMT, NSR of 8 RMT. From this input, it will first compute the NSR as we have discussed previously, and from that it will create the NSRSG for the different cell. And from the NSRSG, it will construct the cycle for each NSRSG. Then it will call algorithm 2. For the algorithm 2, our input will be the rule vector, length of the CA, NSR and set of cycle in each NSRSG. And from the set of cycle, it first consider the compatibility class, then it will find the each unique sequence. If if the sequence of RMT composed of fixed length more than one cycle, then the algorithm will terminate, else it will return the number of fixed point. Next, we have synthesized MSA here. For synthesizing MSA, we have developed three algorithm 3, algorithm 4, and algorithm 5. So what algorithm 3 will do is, it will randomly choose any cell, any rule as a fast cell rule, those having at least one self loop NSRSS. Next, for the rest of the cell, algorithm 3 will call algorithm 4. Then algorithm 4, what algorithm 4 will do, depending on the cell number, whether it is a first cell rule or second cell rule or intermediate second last cell or last cell, it will call algorithm 5 and send the required parameter to create the candidate set for the next cell. Next, algorithm 5 will extract the RMT sequence, and if the number of unique RMT sequence is less than the number of attractor, suppose we require X number of attractor for all the cell, if the number of attractor is less than X, so it will return that rule. And for the last cell, if the number of unique sequence is exactly equals to X, it will return that rule or include it in the candidate set. And from the candidate set, it can choose any rule for the next cell. So this is one example. Suppose we are considering synthesis of 6-length hybrid MSA, and we require 4 number of fixed point. As we know that algorithm 3 will choose one rule randomly, so it will choose rule 0 because it has two self-proof NSRSS 0 and 1. Next, for selecting the second cell rule, algorithm 3 will call algorithm 4, and algorithm 4 will call algorithm 5 and send the required parameter. What algorithm 5 will do, it will create the unique RMT sequence. So 0 and 0, so it is creating exactly two paths, so 0 and 0, and another one is 1, T1 and T2, and number of unique sequences less than 4, so it can be considered as an Excel rule. Similarly, it will choose rule 0, rule 255, and rule 107. And for the last cell, again algorithm 5 will consider rule 0, and it will check that number of unique RMT sequences exactly 4, so it can be considered as a next cell rule. So this is the corresponding NSRSG of the hybrid CA with rule vector 0, 40, 255, 107, and 0, and it is exactly creating 4 number of unique sequence, and all the 4 are corresponding to fixed length attractor. So what is the problem of this algorithm is, so time complexity of this algorithm is exponential. So each time it will consider all 256 rule. If it is compatible, then it will include it in the candidate set, and from the candidate set, it can choose any of this rule. So from this algorithm, we have synthesized the MSA in a linear time. For synthesizing the MSA in linear time, we have only considered 15 TSA rule. We have observed the NSRTD for the all 15 TSA rules, and we observe that all 15 TSA rule can be divided into 8 different groups based on the cycle structure. So in group 1, rule 38, 46, 166, and 174 will be present. Similarly, 8 group will be created based on their cycle structure. What first table is indicating, suppose we have selected one rule from group 1. So next, for the next cell, we can choose the rule either from group 1 or group 2. Similarly, the next table is indicating the class relationship between rule 2 and first intermediate cell. Means if I selected one rule from rule 1, so for the first intermediate cell, we have to choose the next rule from group 1. Third table is indicating the class relationship between the last intermediate cell and the second last cell, and the last table is indicating the class relationship between second last cell and last cell. Means if I selected one rule for the second last cell, if I select one rule from group 1, the next rule can be selected from either group 1, 2, 3 or 4. And we have put one constant for all the intermediate cell, the rule must be selected from the same group. Means for the first intermediate cell, if I selected a rule from group 4, the for the next intermediate cell, the rule must be selected from the group 4. So this is the example of the previous algorithm. Suppose 52 is chosen for the first cell rule, as 52 is belong to group 2. So for the third cell, for the second cell, the rule must be selected from either group 2, 4, 5, 6 or 7. From any of this group, we can select any rule. Suppose 235 is selected as it is belong to group 5 as a rule 2. In the same way, you can select the rest of the rule, and this is the corresponding NSRTD, which is having exactly two fixed length attractor. So this is an example of TSE. So now we have considered three potential area of hardware Trojan insertion. So first one is coherence exploiting hardware Trojan. Here we have developed three hardware Trojan. We have considered processes P1 as an infected core, and in the Trojan activation state, what processor P1 is doing. For the Trojan model 1, whenever processor P1 is performing read request, it changes state to modified state instead of set state. So for Trojan model 2, again we have considered processor P1 as a infected core, and whenever processor P1 is performing a read request, it changes state to exclusive state instead of shared state. So ideally, if there is the cache block is present in the other block, so state must be changed to shared state, but it is always goes to exclusive state. And the last one is whenever processor P1 is performing read request, whenever a processor infected processor P1 is performing a write request, it blocks the processor from sending the invalidation request. So it will lead some incoherent state. So we have implanted the hardware Trojan in the multi-to-sim, and we have run in Splash 2 benchmark program. So what we observed that all the Trojan model are affecting the system performance. Beside affecting the system performance, this lead to some incoherent state combination. So for example, suppose the current state combination is all the cache block is present in all the processor in shared state. So it is a valid state combination. Suppose the infected processor is performing write operation. So my desired output will be in CX, it must be in modified state, and for the rest of the other processor, it must obtain the block in invalidation state. So in the presence of Trojan model 2, 3, what will happen that the infected processor will get the block in modified state, and it will not send the invalidation request. For the rest of the other processor, it will obtain the block in shared state. And effect of the we have, so this is the incoherent state combination, and we have also write down the which Trojan model is affecting this one. So Trojan model is 3 is affecting this state combination. So similarly, all this incoherent state combination is listed here. So what we observe that during the during the execution, this total 16 possible state combination can occur. Case A to H are indicating the valid state coherence. Consider case D. So one case in M state and rest of the other is in invalid state. So this is the valid state combination. So for A to H, these are the coherent state, and for case I to P, it is the incoherent state. So we require a detection unit, so which can classify between case A to H and case I to P. Means whenever the state combination is between A to H, the coherence detection unit must tell that it is a coherent state combination. Whenever the state combination is from case I to P, the detection units must tell us that it is a incoherent state combination. So for designing this detection unit, we have considered cellular automata based tool. So what we have done here is, for a n core system, we have considered n plus 2 length CA. If the processor having the block is M state, it will configure with rule 21. If the processor having the block is O state, it will configure with 105. Similarly, if the processor having the block in exclusive state, it will configure with rule 21. If it in share or in invalid state, it will configure with rule 15. Then we will run this for n plus 2 number of time. Then we'll check the LSB of the attractor. If the LSB of the attractor is 0, it will say that it is a coherent state. If the LSB of the attractor is 1, it will tell that it is an incoherent state combination. But what is the problem is, there is some misclassification happen here. So basically case D and
Suvadip, you have to stop within a minute, please.
okay. So case D and E is a incoherent coherent state combination. But here what is happening?
Hello,
Hello.
Suvadip,
Yes, sir.
you have to complete it within a minute, please. Then
Okay.
I have one small question.
Okay, sir. For the next work, memory transaction inducing hardware trojan, what we have done is we have developed 4 different hardware trojan model that will induce read or write requests. All 4 hardware trojan model affect the system performance. So for mitigate the trojan effect, we have developed a CA based mitigation technique here. And the last one is cache replacement policy affecting hardware trojan. Here we have considered 2 trojan model. So first one is affecting LRU based system, and next one is affecting the LFU based system. So what is the Trojan model here is, whenever in the Trojan activation state, suppose we are considering the LRU based system. So instead of evicting the least recently used block, it will evict the most recently block. So it will affect the system performance. And to mitigate the hardware Trojan, we have developed a adaptive replacement technique here. So in this work, a comprehensive survey has been done on hardware Trojan, many core system, and cellular automata, and we have synthesized the MSCA here, and 3 potential area have been considered for hardware Trojan insertion. And we have developed CA based technique to detect and mitigate the hardware Trojan. Besides CA based technique, we have also considered adaptive replacement policy. For the future extension, we can consider characterization of irreversible CA structure to efficiently model different physical system. And we can also consider different system level hardware Trojan, and we can observe the effect of the hardware Trojan on the system performance, and we can try to mitigate and or detect the hardware Trojan using different technique. This is some of the reference. This is some of my publication. Thank you.
Okay, Shubhadev,
Yes, sir.
what I see that without going through the coherent states or incoherent states,
Yes, sir.
suppose I am having a circuit, IC circuit here.
Yes, sir.
How the Trojan is exposed? How do I know that it is present?
Without going through coherent state or incoherent state.
Is there any possibility
But
that I
sir,
come
we
to
can
know
do that.
that it is present?
Yes, sir, we can do that by doing the side chain analysis. That's why we are considering the system performance.
Okay,
So if
system
the
performance.
yes, sir.
Okay. So regarding coherent states and incoherent states,
Yes, sir.
can you please quickly within 2 minutes?
Yes, sir.
Make me understand.
Okay. So, sir, during the in the presence of hardware Trojan, these are the 16 possibility may occur. So, for you consider the case A. Case A is indicating all the cache block are having the block in a invalid state. So this is basically a coherent state combination. Similarly, case B, all the caches are in shared state. So this is also a coherent state. So what detection unit do is, if the cache block is between A to H, these are all the coherent state combination. So it will tell that this is,
Coherent means expected, right?
yes sir, expected.
Expected. Okay,
So
okay. And the last set is not expected.
yes,
The
suppose
second one.
two.
Second one.
So for a Moisey coherence protocol, suppose two cache block are having the block in modified state. So this is not a valid state combination. So if this type of situation occur, the detection unit will take that this is a incoherent state combination.
Okay. So I invite questions, online questions. Is there any online questions, please? Any offline questions? Yes.
So, Suvadip,
Yes, sir.
hello.
Hello.
Suvadip, what we witnessed that depending upon some coherent and incoherent state,
Yes, sir.
that spectrum is actually using to and it is fed into some automata rules, cellular automata
Yes,
rules,
sir.
and the detection circuit is executing those based on those rules n times you have said.
Yes.
So how many times? That is the first question. And another is it is very interesting. The proposal is very interesting. But I have a question
Hmm.
that if it is an embedded hardware and it is a Trojan, some Trojan is there in this,
Hmm.
and some application or processes, some situations are time critical. So that n number of execution, is there any? It is an NP hard, or it is a definite that within this stipulated number of iteration we can be managed to identify the problem, because if not, in some situation various security hazards it may come actually. I'm talking about very much from an application perspective.
Hmm.
So can you say something about this?
For the first one, suppose you are considering four core system. For a four core system, we have to employ six cell, and it will be executed for six number of time. So for a n core system, it will be executed for n plus 2 number of time. And yes, for a cellular automata system, the overhead will be there, but it can successfully detect. The main purpose is to successfully detect those hardware trojan,
Okay.
but there will be overhead. Yes.
But can I hello?
Hello.
Yeah, can I say something from my side?
Yes, sir.
That it is this kind of idea actually, if we employ this kind of idea when the chip is prepared and the chip is in the design testing phase,
Yes.
before it goes to the real executing the real application for what the chip is supposed to be. If we do that in the testing phase, then it will be a very good idea, I think. Do you agree with me?
Yes.
Because there is, in the testing phase, there is no notion of overhead. We need to identify a Trojan
Yes,
after having an
but main
idea, after
but
having
main
a
problem of hardware
chip
trojan is it
actually.
may not be activated during the
So
post
that
manufacturing.
is one point from my side, very humbly. Thank you. Thank you.
Okay, Shubhadeep, your presentation is over.
Okay, thank you.
Let us go to the next presenter. The next presentation title is Cellular Automata, Chaos, Convergence and Unification. Supreeti, Kamilya.
Yes. Thank you, sir. I'm just sharing my screen. Can you see my screen? Am I audible?
Yes, audible and screen is visible.
Screen not yet.
Okay, okay, I'm trying it once again. Hello?
Yes,
Is my
audible.
screen visible now?
Screen
Is it
not yet coming. Screen not yet.
okay, okay, sir. I'm just trying it once again.
Hello, Dr. Kamilya, your screen is visible, but I think the PPT is not coming.
Okay, okay. I'm now is my PPT
Yes, now it's visible.
visible? Okay, okay.
Yes.
Okay. Very good afternoon, everyone. My name is Supreeti Kamilya, and I am going to present my thesis work that is entitled Cellular Automata, Chaos, Convergence, and Unification. I have done my PhD under the guidance of Dr. Sukanta Das. Okay, so first of all, my objectives are to deal with the divergence problem of cellular automata. That is, we have dealt with the chaos of cellular automata. We have tried to parameterize uniform as well as non-uniform cellular automata for predicting chaos. Why do we need to predict chaos? That is because see, chaos, determining chaos is actually an undecidable problem. Therefore, there is no mathematical calculation or function that will definitely tell that given a system whether the system will exhibit a chaotic behavior or not. That is why what we can do is either we can observe the system or behavior whether it is chaotic or not, or what will be the behavior of that, or we can have some mathematical calculation that will actually parameterize somehow to predict that whether the behavior of the cellular automata will be simple or periodic or chaotic or complex. So, our first problem is to deal with the parameterization problem of cellular automata that will predict chaos. The next problem is to analyze the convergence problem of cellular automata, that is actually exactly the opposite problem of divergence, where divergence dealt with the chaotic part of the CA, whereas convergence deals with the stability of the cellular automata. And finally, in the third problem, what we have done is to see whether we can unify these two types of CAs, where one is uniform CA and another one is non-uniform CA, and whether one work that can be done by uniform CA can also be done by non-uniform CA or not, or the vice versa, that if I perform one work by using non-uniform CA, is it possible to do it by uniform CA? So, we will deal with this problem also in our third task. And finally, we can design a unified system that uses only one cellular automata to perform various applications. So, as my thesis title says that it is chaos, convergence and unification. So, I have dealt with the chaos in cellular automata. So, we need to know what is chaos. See, if here first we have a stable system, and in this stable system all states are stable, all states are 0, and at some point what we have done, we have added one noise or one information, and can see that this information may propagate to its left or to its right direction. But how it will be propagated, whether it will simply propagate to its left or right direction, or it will affect to the neighboring cells, and it will make it in such a way that a chaotic type behavior will be shown. So actually, when in chaos, it says that when we add one information to a stable system, this minute change in the stable condition can reflect massive changes in the system's subsequent behavior. So there is a very famous statement of Lorentz butterfly effect that says that you have a butterfly flip in one place that results in a tornado in some other place. So from this statement we can understand that a minute change in initial condition can reflect massive change in the system's subsequent behavior. So the chaos theory introduces irregularity in regularity. Why? Because there was a stable system at first, then it is introducing the irregularity there, and it obliterates the concept of determinism. It shows that things in nature depends extremely critically on initial condition. That is, in the initial condition, how I am adding something, whether it is sensitive to the initial condition or not, that is determined by this chaotic behavior, and it denotes indeterminacy, impossibility to make long term prediction. So we can see that we have a space time diagram. That means through x axis we have the space, through y axis we have the time downwards, and here we can see that we have added some information at the initial condition in these 4 figures, and this information is propagating somehow. In the first figure it is propagating to the right, in the second figure it is just a shift from right to left, in the third figure we have somewhat information propagation, and it is affecting its neighbors, but we cannot tell that it is a chaotic system because there are some deterministic way, there are some blocks of this information. And in the fourth figure we can see that the information flows and it is affecting its neighbors completely, thus making the system chaotic. So we can see different type of behaviors from this space time diagram, but one can say that by observation also we can check that whether it is chaotic or not, but how long you will observe to understand whether this will exhibit chaotic behavior or not. It may be possible that in the fourth figure, after some execution, it will start exhibiting the simple behavior, but that is why what we need to do, that we need to predict somehow by some mathematical calculation that from this initial configuration, and if it is following some rule, it will at the end exhibit the chaotic behavior. So basically, as chaos in nature is undecidable, by observation it is not possible to understand the behavior properly, and that is why we need a solution, and the solution is to identify the behavior by parameterizing it. This is the motivation behind our work, that we need to parameterize the system so that it does not need only the observation, but we can by only seeing the rules understand that the system is a chaotic system. And we thankfully we have this excellent tool, the mathematical tool Cellular Automata, which is itself a discrete dynamical tool and can excellently exhibit the chaotic behavior or different type of behavior. Cellular Automata is actually can exhibit different types of behaviors. It is a discrete dynamical system, it changes its states depending on some rule. So we have some initial configuration and we apply some rule here, and after applying some rule it starts its evolution, and how the evolution will actually be done or how we can get the behavior of the evolution, that depends on the rules and its neighbors. Therefore it turns out to be an excellent tool to study chaos. Also, another important thing is the cells. There are cells in the cellular automata that actually evolve. and that changes their states. So whether there are only one rule or there are different type of rules, based on that we can divide the CA into uniform and non-uniform CAs. That in case of uniform CA we can apply only one rule, in case of non-uniform CA we may have different rules. In that sense uniform CA is a special case of non-uniform CA. Now when we are talking about chaos, we should know that there are already some predefined ways of just detecting chaos in some ways. So one very standard definition of chaos is a cellular automatic can be said as chaotic if it is transitive, its temporally periodic points are dense, and it is sensitive to initial configuration. So we have already seen that sensitivity to initial configuration is a very important part of chaos, because we were adding one information or one noise at the stable system, and as it is very much sensitive to its initial configuration, it starts propagating and it starts affecting its neighbors, and thus it makes the system chaotic. Also the CA is transitive if and only if for any two open subsets U and V there exists a number such that if we apply the function on the configuration U, it will reach to some other configuration V. That basically means that there are many configurations within this evolution, and if we start from one configuration we will definitely reach to other configuration. Why? There are infinite number of configurations in this infinite system, and in chaotic system we assume that all the configurations are there, and therefore in the third case we can say that a CA has dense periodic points. What does it means? That if we have a period of the configurations, the points denote here the configurations, if the CA has all the configurations, we assume that there are so many configurations that makes it a dense periodic point. So a CA has dense periodic points. Therefore we can say a CA is chaotic according to Devaney's definition if it is transitive, its temporally periodic points are dense, and it is sensitive to initial configuration. Now what we need to find out is the source of unpredictability, where actually we need to focus, that will tell us the source of unpredictability. So as I said, we were adding a bit of information to a cell, right? And then we were checking whether it propagates to its neighbors. Now based on this information flow, we have divided the flow into two parts. One is information propagation, another one is information cooking. Information propagation, for this we need that we will change only one bit of information in a cell, and here it needs to be mentioned that we are taking three neighborhood CA. That is, if we change in one cell, this change will be depending on its left cell as well as right cell. Now if we change one bit of information, we need to check how this change is propagating to its neighbors. So for one bit of information changing, we name the information flow as information propagation. If we change two bits of information, we name it as information cooking. So information propagation basically says that if the state of a cell has been changed, then we will check that how it will propagate to its left neighbor or right neighbor. Sibling RMTs are, suppose 0 0 0 is the states of three cells, and if we change it to 0 0 1, these two states basically 0 0 0 and 0 0 1, these are the RMTs, and this set 0 0 0 and 0 0 1 is the sibling RMT. And what we can see here, that from 0 if we change it to 1, and suppose for 0 0 0 we obtain the function value 0, and for 0 0 1 we obtain the function value 1. That means what? This change in the rightmost cell is affecting its exactly left cell. So there is a change, and we mark it as 1, otherwise it is 0. And by marking all such RMTs for a rule, and by marking all such rules in the cell, we can get a parameter of this left propagation. Lambda p denotes actually the left propagation, that is equals to 1 by d square. The d is the state of the CA, summation of j equals to 0 to d square minus 1, and the value a actually determines for the change of all the sibling RMTs. So here in the right side we can see one figure where we have added one information, and for adding this we have checked that there is a left. For adding information to the right, we have the information change at the left, and by calculating this we have obtained that in case of rule 102, this is an elementary rule of two state three neighborhood cellular automata, we obtain here that the value of this left propagation is 1. Next one is information cooking. See here, in case of information propagation, we have added one information, right? That means what? We have changed the state of one cell only. Now in information cooking, what we will see, that when this left neighbor or right neighbor is updated in reaction to the update of cell I, that means here we were changing 2 bits of information. The cell I will further be updated in next time step in response to the updates of its neighbors. We call this fact as information cooking. See again in this figure of rule 102, we had information propagation to the left. This change in the information propagation, this change in the cell in turn is changing its right cells, and thus it is making the system chaotic. So the right cooking value is basically is 1 by this calculation. Now another point we have established here is the communication between two cells. Suppose one cell I is communicating the other cell J. So we establish one relation that is called communication relation, and we have defined the relation. A communication relation is a relation where I communicates with J holds if the right propagation is greater than 0, or the value of right cooking is greater than 0 for the cells I plus 1 to j. Second point is the left propagation is greater than 0 or the left cooking is greater than 0 for the cells I minus 1 to j, and both are true when I equals to j. Now suppose one cell is communicating with another. If somewhere there is no communication, if the communication is blocked, then we cannot say that this is a chaotic system. That is why to be a chaotic cellular automata, what we need to have a communication among all the cells. That means what? This relation should be an equivalence relation, and it should form, all the cells should form a single equivalence class. We name it as communication class, and we have newly defined the cellular chaotic cellular automata apart from Devan's definition of cellular automata as a CA is chaotic if and only if the CA is transitive and all the cells of the CA form a single communication class. For rule 30, we get, for example, the left propagation is 0.5, the left cooking is 0.5, right propagation is 1 and right cooking is 0.5. Therefore, it is also transitive and form a single communication class and also a Devan's chaotic. Now, we are coming to the parameterization part.
Excuse me, Supreeti, you have 2 minutes more, please.
Okay,
Finish
sir, okay.
within 2 minutes.
Okay, sir, okay, I am wrapping it. So we have parameterized based on the value of right propagation and left propagation and right cooking as well as left cooking, where we got these two parameters that will determine that if the value is higher, then we will say that the system is chaotic. If it is lower, then we will say that the system is not chaotic. And the next problem is dealing with the convergence problem of cellular automata, where we have taken the finite non-uniform CA and we have used a tool reachability tree, and depending on this reachability tree we have proposed some theorems. For example, one theorem says that a CA is not an SACA. SACA means single attractor cellular automata, that is a convergent cellular automata, if there exists no self-linked edge for an RMT at ith level of the reachability tree. And this is how, from this reachability tree, we can understand whether a CA is a convergent CA or is not a convergent CA. And the third problem is simulating one non-uniform CA by uniform CA, and how we were simulating it by using some function I. If we have a function I that that can say that suppose I have 90 and 150 rules in the non-uniform CA, and we form a rule in for uniform CA, like 90 and 0 will be 0 for uniform CA, 90 and 1 will be 1, 150 and 0 will be 2, and 150 and 1 will be 3. So there are 4 states in the uniform CA. Now we can construct this uniform CA that can actually simulate the non-uniform CA. This non-uniform CA can be constructed by any combination of these rules 90 and 150, and by applying this theory we can have this application that is shown in the right side of this figure. This is the unified system. So previously with the non-uniform CA, with the 4 different non-uniform CAs we can have 4 different applications. One is PRPG, one is data encryption, one is code data compression, and one is error correcting code. Now we can have only one uniform CA. We do not need to find so many non-uniform CAs to do this, and with this one uniform CA we can apply on all these things to perform all the applications. So the future scopes are finding more solution to predict the chaotic nonlinear dynamics, and finding parameters for the higher dimensional CAs also, and a detailed study on the convergence problem for non-uniform CA. My undergoing work is to predict the chaotic non-linear dynamics using some other ways. That is, we are currently using recurrent neural network, and within which eco-state network that can predict the chaotic behavior of nonlinear dynamics. And another undergoing work is application on grade and thickness estimation of minerals in mining industry using cellular automata. These are my publications. I would like to thank my supervisor, Dr. Sukanta, Sir, Dr. Biplav Kumar Shikdar, and all other my teachers and my colleagues and my friends for helping me out in completing my journey in PhD. Thank you, everyone. Thank you all.
Thank you, Supreeti. Nice presentation.
Thank you,
Let
sir.
me ask you to. I would like to get an answer from you somewhat intuitively. Suppose in a number of cells, okay,
Yes.
non-uniform and non-linear rules I am applying. Okay, you
Non-uniform
have
and
started
non-linear.
your
Yes.
definition. You have started your definition after initial configuration. If determinism is lost, then it becomes
Yes.
chaotic. Are you agreeing?
Yes, sir. Yes.
Okay, so if it is non-uniform and non-linear, different non-linear things. Okay, so next evolution is totally, suppose, unpredictable.
Yes.
Is it chaotic? You are
Uh,
developing science, I know. I have seen your presentations, publications, but I would like to get one answer from you. So, in this context, what is your observation?
My observation is, sir, actually, yes, if it is unpredictable, we definitely go towards the chaotic system. But one another thing here is that we need to also check whether this flow of information gets blocked or not. If there is a information that blocks somewhere for the blocking word, then we cannot say that the system is chaotic. If we apply non-linear CAs as well, so sometimes I have observed that I am not saying that no nonlinear CA can exhibit chaotic behavior, but sometimes we have seen that using nonlinear CAs makes many blocking words. And if we have blocking words in the system, then we say that this system is not chaotic actually.
Okay. Okay, any other questions, offline or online? Online questions, okay. Please, online questionnaire. Hello? Dr. Rezki Shemlal, please.
Hello, everyone. Do you hear me?
Yes, yes, audible.
Okay. I have, first of all, thank you for your presentation. I was
Thank you, sir.
just wondering, when you apply you are talking about non-uniform CA and still, I
Yes.
think, applying Devan's definition of chaos. So when you
Yes.
apply non-uniform CA, do you have still some form of continuity?
Sir, actually, in case of non-uniform CA, yes, we have taken the non-uniform CAs like suppose we actually know the sequence of the rules when we are applying the non-uniform CAs. Like sometimes maybe the rules are periodic, like 90 150 90 150 like this, or sometimes we have applied that at the left side we have some rules and at the right side we have some rules. Anyhow, we need to know the sequence of the rules, and there we have applied the functions for each cell, for each rules, actually for the sequence. And if for the sequence we get the higher value of the parameter, we say that the system is chaotic. And it
Okay.
is also applicable for Devan's chaos definition also.
But I was wondering something, I think, more basic. You know, when you think about uniform CA, so we have the continuity of the global rule, as we are used, I mean, in my domain, we are used to say that to have dynamical systems, you need some form of continuity, or and if you throw away continuity, you will lose some basic results in dynamical systems. I was wondering if when you go to non-uniform CA, does the global rule as a function from the space of configuration to itself, is it a continuous map or not?
Yes, it will be. It is a continuous map when we are also applying it in case of non-uniform CA, because for all the rules, basically we are applying it on each cell, and we know the sequence, and that is why we can have a mapping from one to one mapping actually there.
Okay. I wanted also just to point out that in Devan's definition of chaos, you do not need. I don't know if you are aware that you need just transitivity and dense set of periodic points to imply sensitivity. But I think you still need sensitivity as as an indicator of chaos.
Yes, actually, what we have done, we have somewhat shifted from Devan's definition of chaos in the sense that we have only taken those CAs that intuitively we understand that exhibits chaotic system. For example, ECA rule 170. According to Devan's definition of chaos, actually it is a chaotic CA. But according to our definition, we have not considered it as chaotic CA because there is properly a shift from right side to left side. Therefore, according to what human brain perceives, only we have considered this behavior of cellular automata. That is why we have little bit shifted from this definition of CAs, and we have established this communication relation to define it newly.
Okay, thank you so much.
Okay, thank you, sir.
Is there any other question? Any other question, please? Okay, in the event of no question, so I conclude this first session, and Supreeti, your presentation is over. Thank you.
Okay,
Thank you very much.
thank you, sir.
Thank you, Professor Povitra Palchaudhuri, for this informative session. We are ever thankful to you for attending ASCAT 2023. On behalf of the organizing committee, I'd request Dr. Sukanta Das to present Professor Palchaudhuri a small gift. With this ending morning session, it's time for lunch break. We shall assemble here at 2:30 p.m. After the break, online participants are also requested to join at the same time. Thank you.